Well, I could call her. I have my phone. So the old one doesn't work anymore? What? Huh?
This one does though. I really don't know why.
I just wanted to wish you all the best.
Excuse me?
I just wanted to wish you.
Oh, thank you so much. Yeah.
I put a link here
Uh-huh. Oh, okay.
so they can go to that one if
That's
they
good.
can
That's
they can see. Do you want to type it in Polish or something?
Can you make it like really large? You can't. It's okay. We'll figure it out.
I thought I could add
Yeah, that's where I can write to.
right.
I think like a really eye-catching, then it's gonna.
You type something in Polish real quick, and then
Yeah.
if I can figure out how to get a big banner, then. Sorry. Have you?
What's the new one?
That one.
Can I just copy it or?
Yes, perfect.
Well, that's not. Can you just put the link here? I don't think that's the actual link.
This one will work. So.
Yeah, I think it shortened it when you copy it.
Oh, okay. Damn. Now it works.
Oh, hi, Carl. Yes, hi, Carl. Yeah, I can hear you. So I'm going to try to share my screen. Is this working? Do you see my slides? Okay. Is this okay? Oh, okay. All right.
Okay, that's so amazing. This is actually it was super nice. Yeah. Gotta ask some questions. In general,
I think all of us are looking already.
Is this better? Hello, Harold? Okay, so you're seeing my slides. So,
This is Maria's.
okay.
Hey, Carl, Dan here. I just wanted to say hi and thanks for getting on. We'll talk more after the presentation. Great, thanks.
Hey, I'm leaving soon. Well, you know I'm here.
Okay, how you doing? I know, it's not that. Congrats.
Don't worry, it's no questions.
You're not questioning that. So, you're talking about now. Yeah. Yeah, but they didn't sell that. It seems like the chamber. Maria's got some ideas. We're talking about the laptop.
Oh, yeah.
Maria's got some ideas about how you use that properly.
It's not this presentation.
Think about it for
I
you didn't know that was graduate school, so.
didn't either.
Yeah, and department, I was actually there last year.
Like the.
Yeah. I tried to tell him, I think he's. We'll just give it about 2 more minutes. And start. Yeah. So let's go ahead and get started. It's my great pleasure today to get to chair, but also be advisor for Maria Zawadowicz's defense. Maria joined us 5 years ago. This is almost, I guess, going right on her 5-year anniversary. And I remember that I first met her about 6 years ago. And it was because I was introduced to her by her former undergraduate advisor at Lake Forest College, which is a suburb just north of Chicago, Illinois. Maria's undergraduate advisor, somebody that she worked with, is Lori Del Negro, who a lot of us know in atmospheric chemistry quite well. And she was telling me about this fantastic student that she had who was looking at graduate school out of chemistry there. And I thought, you know, I had grown up in the Chicago area, so I knew that this was an outstanding undergraduate school and had a great chemistry program. And I started searching around on Maria, so like as we all do, you gotta Google Maria, try to figure out what she's all about. And the first thing that popped up was Maria over a soldering bench working on electronics with a soldering iron. And I went, bingo, there's a graduate student, you know, on laboratory equipment at MIT. And so we were very lucky to have her join us about 5 years ago. And what you're going to hear about today is sort of a culmination of the last 5 years, a number of fantastic projects that Maria's worked on, everywhere from developing and building new and better instruments for the measurements we make, all the way to the atmospheric implications and a better understanding of what we can do. I will just close very quickly with something that the admissions committee said to me. If you guys know my last name, it's CZICZO. And when I mentioned that I was very likely to make Maria an offer, they pointed out that that would be too many C's and Z's in one group. But nonetheless, I think it's worked out very well. So with that, I will just remind you of the format. This is going to be an open defense. Maria's going to speak for about 40 or 45 minutes. And then her committee will take questions from the audience. The committee will largely remain silent. We have a very silent partner, Carl Freud from NOAA, who's on Skype right now. We'll try to hold our questions unless they're very important. We'll open it up to you guys for question and answer. That'll take us to about the 1 hour level, and then we'll let you guys go. We'll close the doors, and we'll continue with a closed committee session at that point in time. I'm good? All right. So, Maria, the floor is yours.
Thank you, Dan. I just want to confirm, Carl, do you hear me well?
Yes, I do.
Thank you. So this presentation is about understanding chemistry of atmospheric particles using simple particle methodology. And I added a subtitle because we tried to gain an improved understanding of climate by using these novel mass spectrometry techniques. And by the end of this talk, I hope I'm convinced you that we in fact have. There are several reasons to study aerosols. One of them is rather dramatically illustrated here. This is Beijing in China, and it's one of the cities that has a problem with something called PM2.5 pollution. These are particles suspended in the air with diameters less than 2.5 microns, and they contribute to this bad visibility issue here. But they are also very harmful to health. This is a compilation of different studies in different cities, all of which are, in all of which this PM2.5 pollution exceeds the regulations of the World Health Organization. And on the x-axis is the estimated daily dose of this PM2.5 pollution, and on the y-axis is the adjusted relative risk of various diseases, like the cardiovascular or cardiopulmonary disease. And unfortunately, people who live in those polluted cities have a higher risk of developing health problems than those who don't. This is one reason, very important one, and another one is that those particles influence climate. They can change the relative properties of our atmosphere. Here is a figure from the IPCC, the recent IPCC report, which summarizes the relative forcings by different things in the atmosphere, like gases and particles. And if you compare the error bars for these estimates, those for gases are much smaller than those of particles because those effects are much harder to model. There are two effects, in fact. One of them is the direct effect. It is when particles in the stratosphere and upper troposphere scatter incoming solar radiation. And here is a plot also from IPCC that summarizes the direct effect, the total direct effect, by composition of the aerosol. Now here, sulfates reflect radiation, and black carbon absorbs it. And what the takeaway message from this is that composition matters here. Now, the second effect of aerosols on climate is the indirect effect. And this is when aerosols help to form clouds. And those clouds, in turn, change the relative properties of the atmosphere. Aerosols can make liquid or ice clouds. For liquid clouds, an aerosol particle will attract other molecules from the gas phase. It will grow into a small droplet and then grow further into a liquid cloud droplet. The process is described by something called the polar theory. Here are several polar curves that describe this growth, summarized by particle diameter and composition. As you can see, the composition matters for this process. Now, we also have field studies of this. This is two pie charts where an airplane is flying through clouds and sampling both the ambient aerosol outside of the cloud and cloud droplets, the content of cloud droplets. Now, talk a little bit more about how these measurements are made. But for now, that we pointed out to you that sea salts are greatly magnified in the liquid cloud droplets because sea salt is really good at making clouds. That has a lot to do with its hydrostaticity. For ice clouds, the story is a little bit more complicated. This figure illustrates a phase space of supersaturation with respect to ice and temperature in Celsius here. There are certain pathways to making ice in the atmosphere, and it can occur straight from the gas phase without an intermediary particle, but this requires high supersaturations and low temperatures. For the vast majority of ice nucleation in the atmosphere, a particle acts as a seed that ice crystals grow on. It's called heterogeneous ice nucleation, and this particle is an ice nucleating particle. We have also some field studies of this. These are 4 campaigns summarized, and the story is very similar. An airplane flies through clouds. This time these are cirrus ice clouds, and it samples those ice crystals, but also samples the clear sky aerosol without the cloud. The comparison prides are rather striking because those ice crystals contain particles that are completely different from the clear sky aerosol, and they are very enriched in this brown component, which is mineral dust and metallic components. So crustal components as well as heavy metals, industrial pollution. I wanted to talk a little bit more about how we actually make these measurements, because this is what I have been working on. So everywhere in our atmosphere there are aerosols, and we can sample them, and we can find out their chemical composition. Sampling clouds is a little bit more complicated. For example, in this upper part of the atmosphere, this is, let's say, a cirrus cloud made completely of ice crystals, and the airplane is sampling the ice crystals. We need an extra step here. It uses a special inlet called the contact virtual impactor, and its function is to separate ice crystals from interstitial aerosols around the crystals. It then evaporates the ice crystals, and what's left over is whatever particle nucleated this crystal, plus any other component that the crystal scavenged along the way. We can do this from an airplane. We can also do this from a high altitude station, where clouds will have a mixed composition of ice and droplets. We'll use a similar inlet for this. And we can also do this from lab, where there is no clouds, because we can use a cloud chamber. To sample, we can sample aerosol, ambient aerosol. We can expose it to a desired set of supersaturation and temperature conditions, make a cloud, sample it, and then get ice or liquid residuals. But the terminal step for each one of these is the chemical composition analysis, and this is why it is so important to improve those techniques. I want to bring your attention to the fact that we need single particle resolution for cloud studies, because every ice residual will be different, and we want to study them one particle at a time. It is also helpful for other applications. For example, these two mixtures, an external and an internal mixture, cannot be differentiated if this aerosol is just collected on a filter and sampled in bulk. Only a single particle technique can differentiate between those two mixtures. Historically, measurements like these were made using electron microscopy, and a data product from this technique is an EM image. And there's also an associated technique where the electron beam is used to collect EDX spectra, which allows us to do elemental composition. And those elements that appear here, this technique is quantitative. So we know we can tell how much of each element that this spot contains. It is a single particle technique. It is a single particle technique because every image is analyzed one at a time. However, those samples have to be collected in the field and then transported, and that is fraught with problems of sample loss and contamination. And it is very labor intensive. An EM microscope cannot be taken on aircraft. Now, on the other hand, there is this modern method of single particle mass spectrometry that we work with. This is our instrument in lab. The data product is a single particle mass spectrum for every particle. It shows which ions are extracted from this particle, and I will talk a lot more about this. We have single particle resolution, one spectrum per particle. We are sensitive to both refractory components such as mineral dust or elemental carbon, and volatile components like organics. And we can take these instruments to the field. We can also deploy them on aircraft. Now, on the other hand, spectral interpretation of these mass spectra can be a little challenging because in addition to atomic components, the ions that appear here often contain atom mixtures or atomic clusters. And in complex atmospheric particles, this is not always straightforward to interpret. It is also not completely quantitative. By looking at this chlorine peak, I cannot really tell you how much chlorine there was on the particle because ionization potentials differ depending on the particle matrix, the bulk of the particle. This is the instrument that we work with. It's called particle analysis by laser mass spectrometry, or PALMS. It samples particles through an inlet called an aerodynamic lens. Particles cross a laser beam, giving out a scattering pulse, and then another one. And then this event triggers another laser to fire, vaporize the particle, extract its ions, ionize it, and then the electrostatic field drives the ions through the mass analyzer. The mass analyzer in this case is a long evacuated tube. The ions hit a band here, they bend before they get to the detector. That is important because this ionization laser produces very high energy pulses, which make the ions, which gives the ions a broad energy distribution. And by using a band, we can cancel some of this out, and this will become important later. PALMS also measures vacuum aerodynamic diameter, because as the particles cross two laser beams, we can measure their speed and therefore their aerodynamic diameter. And PALMS targets ambient size distributions. These are 3 distributions from satellite measurements. Notice that they are with respect to aerosol volume, that number. And we sit right in this range, from 200 nanometers to a couple microns, where a lot of atmospheric processes are very important, like cloud formation. Additionally, here is a size distribution of ice residuals at the high altitude Alpine research station. And we are very well positioned to measure ice residuals with respect to size. So for this talk, I'm going to talk about several instrumental improvements that we made here to the existing system. We looked at ionization laser as well as the mass analyzer. And then for the second part of the talk, I will talk about whether or not we can apply this improved methodology to a contemporary problem in atmospheric chemistry. What can these measurements tell us? So starting off with ionization laser, I want you to consider this spectrum. The spectrum has been obtained by a technique called matrix-assisted laser absorption ionization. It's a spectrum of an E. coli bacterium. And if you look at the mass scale here, it goes up really far. This is because these peaks are not just atoms or even clusters of atoms, they are whole molecules. In particular, these 2 peaks show the exact peptide sequence that this bacterium has, which helps in identification. This is what we call the soft ionization technique. It means that it does not fragment molecules very much. But this is not what we do in the atmosphere. These are very expensive and non-portable facility instruments, and they require very, very extensive sample preparation. So, but this is the one extreme of what we can do with laser ionization. On the other hand, I would like you to consider this mass spectrum, where we have carbon and oxygen, we have sodium and chlorine as well. And these are only atomic ions. They were produced by ionizing this polymer in an NaCl solution. And in this spectrum, the ratios of these elements correspond exactly to the ratios of carbon and oxygen in this polystyrene molecule. This is quantitative spectrum. It was obtained by a high-powered laser that makes plasmas. And this is an example of a hard ionization technique. So we have 2 extremes in laser ionization. And our technique, PALMS, lies somewhere in the middle here. towards the harder part of the spectrum. We wanted to find out whether by changing the Pond's ionization laser, which currently is at 193 nanometer UV laser, if we change that to a femtosecond laser, can we achieve softer ionization? Can we make the spectra easier to interpret? So we have done just this in collaboration with Karlsruhe Institute of Technology. We put a femtosecond laser into Pond's using its existing optical setup, and everything else on the instrument remained the same. We obtained spectra like these. These are of NaCl, this traditional versus femto. And the one surprising thing here is that on the first glance, this is the same mass spectrum. However, there are a couple of details that actually separate them. For example, there are some molecular chlorine ions deposited here that do not appear normally. This allows us to determine that these techniques provide a very similar kind of ionization, except femtopomps is shifted a little bit more towards the hard ionization side of the spectrum. So in conclusion, from this part of the experiment, we have learned that an unexpected fact that we cannot induce softer ionization using femtosecond lasers. However, we now have a methodology. We have now a technique. These were the first femtosecond spectra collected. And this shows a lot of promise for particle depth profiling. With short pulse laser like this, it is possible that we can profile particles one layer at a time. Now, as a secondary instrumental improvement, we have also experimented with a new mass analyzer in order to make, get spectra with higher resolution. Here's an example of a Pond's spectrum, which has lead on it. Also has zinc. Zinc has 4 isotopes that are pronounced here. And now lead also has 4 isotopes, but these are not visible here. It's a broad peak, and this signifies a loss of resolution at high masses. Is there anything that we can do about this? We have used, so as I have alluded to before, an ionization laser on Pond's imparts broad initial energy distributions to the ions. Now, as the ions travel through the fly tube, we can correct for some of this because a slow ion will take one path to the bend, and a fast ion will take a slightly longer path through this bend for the reflectron. And by the relative difference in paths allows us to correct for the initial brown peaks. But we can do this better. This is a design that was developed at NOAA. And this path is slightly different. Ions fly like this. This is called the S-stop. There are 2 bends here, which are better than the one bend. And those bends act as bound turns for the ions. We have seen an immediate improvement in resolution by adapting this design onto Pond's. So here is a previous lead spectrum in red, which does not have horizontal peaks, and a new lead spectrum obtained with the S-stop, which has 4 very clearly resolved lead peaks. This works for other elements, not just lead. This is an interesting example, as previously it is not clear here that this part of the spectrum is made up of 2 chemical components, but by using the S-stop, it is clear that there's a lead and a thallium here. Here is another example with barium. Previously, the barium isotopes here were not clear. They were lost in the baseline, and now they are. And my favorite example is tin. It has a very fine, interesting isotopic structure, which is now better resolved. Here is a quantification of how much better on the resolution we can get. For high masses, we can get about half as we can get a resolution improvement of about 50%. Here on this y-axis, there is peak width, and peak width corresponds inversely to resolution. So anything that decreases here has better resolution. The reflectron is in black, always on top. It has worse resolution than the S-stop. Points that fall here, they're always at a better resolution. This differs a little bit depending on the particle composition. I have done elemental sulfur here and elemental carbon. But the resolution improvement is visible in both polarities. So we have demonstrated a significant resolution improvement with DS stuff. And additionally, we have found there is some promise for doing isotopic ratio measurements. Here is a plot that we did using an ensemble of ambient particles that contains tin. And those spectra where we have quantified the isotopic ratios of tin, as shown on one of the previous slides. Here are expected rate at natural tin isotopic ratios. Here are measured ratios, and the correspondence is actually pretty striking. We are still exploring those measurements. We have started a collaboration with Shuhei Ono in this department to do the same thing for elemental sulfur. So finally, there comes a time for the second part of the talk, which is whether or not we can apply our improved methodology to a contemporary problem in atmospheric chemistry. And I'll sketch out the problem here. And it refers to abundances of biological particles or bioaerosols. Those are particles that are derived from biological matter in the atmosphere, such as bacteria, fungal spores, or pollens. This plot shows a model distribution from a paper of bacteria and fungi, which shows clearly that this model has predicted that there is an abundance of bioaerosol in the atmosphere, both bacteria and fungi. It is much different from a concentration of something like dust. But there is a distinct lack of measurements of these particles in the atmosphere that is really hard to verify and compare to the models. We wanted to see whether we can actually derive biological particle concentrations using our technique. So here emerges a problem, and the problem is illustrated in these three spectra right here. On the top, we have a spectrum of Pseudomonas syringae. Here is a spectrum of apatite, which is a mineral that contains phosphate, and similar monazite, also a mineral that contains phosphate. Those particles share four spectral features: organic nitrogen, CnO, and phosphate, PO2, PO3. And in the literature, those four markers have been historically used to identify bioaerosol. However, all of these three spectra share them, and this is therefore not correct. So can we improve on this? And by an analysis of a big library of single particle mass spectra that we have acquired in the laboratory, we have determined that we can actually use ratios of these peaks, create a biological identification technique. And I'm going to describe how we did this right now. So we have looked at the ratio of PO3 to PO2 ions. We have plotted it on a histogram like this. For apatite, those ratios distribute very, very narrowly here. Similar story for monazite, for fly ash, for agricultural soil dust, which was a natural sample acquired in Germany, which had also contained man-made inorganic phosphate fertilizer. Now the story changes for bioaerosol. Now here are Pseudomonas syringae bacteria, fungal spores, oak pollen, and as you can see, a clear distinction emerges just using those two ratios. This simple one-dimensional classification has already 80% accuracy. However, we can do better than this. Statistical techniques have easier time drawing boundaries between clusters in 2 dimensions, so we added on the CN to CNO ratios because, as you have seen from the first plot, the existence of those 4 peaks is unnecessary but not a sufficient condition for identification of bioaerosol. So all of our lab samples are plotted in green. Every point on this plot represents a single particle mass spectrum. All of our inorganic lab samples that contain phosphate are plotted in black, and 2 clusters clearly emerge. We have used a a machine learning technique which solves optimization problems by drawing boundaries between clusters to draw a boundary between those two clusters. And right now what we have here is a binary classifier phosphate of inorganic origin. If I have an atmospheric particle of unknown origin, and if it contains phosphate and organic nitrogen, I can put it on any point in this space, and if it falls here, I've got a biological particle, and if it falls here, I've got an inorganic particle that happens to have phosphate. Now, these continuous lines are uncertainty boundaries that we delineated. It's about 80% uncertainty. If a particle falls within this boundary, its identity is unknown, or uncertain. Okay. This has overall 97% classification accuracy for known lab samples in this training set. And the final question that we asked here is whether or not we can apply this to field data. That's the fun part of this. We have acquired many data sets of field data with ponds. So this is the version of our instrument at NOAA, which flies on aircraft, as well as the version of the instrument here that we have here in lab, which is still field deployable, but does not fly aircraft. Here are results from 2 different ground stations. This is Storm Peak Lab, Colorado, and a site of a campaign called CARES, Carbonaceous Aerosol Impact Study, on the foothills of Sierra Nevada mountains. And from these 2 ground sites, we see that there is bioaerosol here. I will show several plots like this, and the convention always is that bioaerosol is in green. Inorganic phosphate with inorganic phosphorus is in black, and silicate minerals are in brown. Now, hatched parts of the bars signify mixed composition, with bioaerosol is mixed with silicate, and inorganic phosphorus also can be mixed with silicate. So in the ground station data, we see that there is a significant proportion of bioaerosols here near the near surface, decays as we go up. This is CARES data, this is FIM3 Storm Peak Lab data. But there's also a significant proportion of inorganic phosphorus that previously would have been classified together with the bioaerosol. Now note the scale on the silicate minerals, which is 10 times bigger. There's a lot more, this material is a lot more abundant in the atmosphere. But even more fun, we can do this with aircraft data. And now all of a sudden we have a lot more places to look. These are 4 flight campaigns that Flight Ponds was involved in. And here as well, we see that there is bioaerosol in all of these plots. There's always a constant background of bioaerosol. It is usually less than 1%. Here, this MAPEX campaign was exceptional because it had a lot of coarse material. These campaigns cannot be really directly compared to each other because of different seasons when these were carried out. But they all have bioaerosol. They also all have inorganic phosphorus, so highlighting the fact that this material may have been misclassified, and that now we are hopefully getting a lot more accurate estimates. Here in the upper parts of the atmosphere, above what we said is cirrus altitude, we have seen that silicate dust is about 30 times more abundant than bioaerosol. So now we can compare our measurements to modeling data. As you can see, we have already seen that silicate dust is much more abundant. And we are working currently with Collide Fields Group on making the comparisons even better. So in summary, for the bioaerosol part, I hope that I have convinced you that great care must be taken when interpreting the results from our techniques from the mass spectrum. Simple treatments can lead to very large estimates. Our improved technique now can be deployed, and it detects about 30 times less biological aerosol than mineral dust at cirrus altitudes. And overall, for all the field campaigns that we looked at, the background bioaerosol concentration seems to be less than 1% in the Palm's size range. It is consistent with most electron microscopy evidence. And because this was the final part of my talk, I have some overall conclusions to this. It is, so as you have seen in the femtosecond part, we have shown that femtosecond laser ionization mass spectra show very little difference in fragmentation patterns compared to traditional Holmes ionization. However, this technique offers promise for depth profiling, and we have learned something new. In the second part, I have shown you that using the new S-Stoff mass analyzer considerably improves the resolution of single particle mass spectra. And it offers further possibility of doing accurate quantification of isotopical abundances. And finally, Holmes spectra of bioaerosol can now be identified using our new binary classifier. We have achieved 97% classification accuracy rate. And finally, you can apply this to field data to derive vertical profiles and to put this data into models so that we can say something about bioaerosols in our climate system. So finally, I would like to do some acknowledgements at the end. So this has been a result of 5 years of hard work. So first of all, I'd like to acknowledge my advisor, Dan Zitzel here. He's been just instrumental in getting this project off the ground and through all his advice. And I really enjoyed working in his lab. My committee, so Carrie DeHoy, Jessica Kroll, and Paul Freud, for their input on this work throughout my career, and further I hope on the pieces. Collaborators of Noah, so Dan Murphy actually designed the S-Stoff, and generously provided it for us so that we could use it for the S-Stoff part of the work, and he was also very invaluable with his expertise on single particle mass spectrometry for all of this. There are some collaborators at KIIT involved in this. Thomas Leisner, Claudia Moore, Clark Zabov, and Ahmed Abdelmonem, who I worked with on the femtosecond part of this work, as well as the AIDA staff and the Stormy Lab staff, where some parts of this work were carried out. The funding that I have received was also obviously instrumental here. The Zitzel group members were like my second family here, so I thank them as well. And my friends and family, honestly. So thank you so much for listening to this.
Although that was a great talk, don't go easy on Maria. So make the final part of her defense nice hard questions. Sarah, would you start us off?
Thank you. Nice show, experiment, hypothesis, and computation. Okay, so my question for you is about machine learning. Could you have done this another way? Was it just a handy tool for classification, or did it truly add insight that you couldn't have done with another computational technique?
That's a very good question, because in this case it was, yes. We found that those machine learning techniques actually allow us to derive very accurate classifications. Were not deployed on this type of data before. We actually think that in the future they will be very, very useful. We use
Dan did ask me to push you, so what example you showed?
Yeah.
Like I feel like I could have, I know this sounds very trivial, I know this isn't meant to be that's anyway, but like I could have just I could have done that by eye. So the question is, a lot of fields, they're using machine learning, it's the buzzword, it's convenient and quick. But I'm wondering if there was another approach you could have taken to get the same answer.
Yeah, there are other computational techniques. Part of it was an overall interest in them because they are very prominent right now. And we're also treating this as a stepping stone to some further analysis, because these are only two components, two ratios. But mass spectra like these contain a lot of information. Not all of this information is useful, not all of this information can be mined for something like this. But there's a lot of information that we can use, and not everything, we cannot do everything by eye if we have.
Right, that makes sense. It's like a stepping stone to like
3D or 4D or 5D.
As a committee member, I'm supposed to wait for later. However, I'm going to violate that right now. And there was something that you alluded to earlier. I think that you could answer Sarah's question. So why did you choose these two particular ratios as opposed to opening up the entire phase space in this machine learning problem you did?
Yeah, that is a very good question. I wanted to stay consistent with previous literature because CA and CNO, PO2, PO3 are everywhere in literature cited as biological markers. And one of the One of the great insights of this paper was to show that it is not true and we need to be more careful. Also, phosphate was important here because phosphorus does not undergo gas-phase chemistry in the atmosphere, so its presence on a particle constrains its source, so that we can identify phosphate-containing particles and we can narrow down this inorganic phosphate space very well.
So if I understand your results in the last part correctly, you found some pretty dramatic changes in the abundances of fire aerosols.
Yeah.
But does that change how we understand the formation of fire aerosols and their importance for clouds, or is it just, will it not result in a significant change in our understanding of clouds?
Oh, that's a great question. It's something that I didn't quite get to in this talk, and it's important. So bioaerosols have been hypothesized very heavily to influence formation of ice in clouds. Certain species of bacteria can form ice at very high temperatures, so -10 or -15. So it's been hypothesized they're important for first ice formation, but we don't really have insights into this from many field studies. There are the cirrus residual or ice residual measurements are shown at the beginning. Those are very rare studies. And because we don't have any field insights, we can't really model these abundances very well. And also, we can't really say how much of an influence it is. We hope that deploying this technique on a very extensive data set from homes, both in ground and in the aircraft, we can actually improve the models, and we're working on that before.
So when you were doing the work on the femtosecond laser, you saw that, maybe against the first thoughts, it ended up being a harder ionization technique. Do you know of any techniques or any lasers or any way to get toward that softer design way? Maybe not directly related to what you've done now, but where do you see the sort of frontiers of that, or how would it be possible to get softer ionization in single core?
Yeah, that's a very good question. So there is some work from the 8FMS side of the spectrum. So 8FMS is a different instrument from COMS that uses very similar principles except a different ionization laser. It has a longer wavelength and the focusing spot is a little bigger. And it seems like they can get less fragmentation on some very stable things like aromatic systems like PAHs. But it still fragments significantly. So right now, short of using actual solvent or matrix like azimuthal, I don't really see how we can do this.
Bobby.
Since you were mentioning other single-party mass spec parameters, and going back to the very first question, so how easily extrapolate your findings to any other instrument, or how strongly is your other findings to be constrained to the COMS instrument and the mass spec that you're using?
For the bioaerosol specifically. So it's actually, as shown, the classifier is form specific. I would not copy this exactly into the 8FMS or flat for that kind of world. Laser ionization is very sensitive to certain instrumental parameters, like the laser power that you use on it or laser wavelength. Now, this could be done, the whole experiment using different lab standards could be repeated for 8FMS. They would end up with a different classifier, but I think something like that could also.
Yeah, did you have a question?
Did you distribute the network to classify bioaerosols?
Yeah, so it's actually done in the field. There's an analysis based on neural network. We do also do it for COMS. We've been machine learning because it's honestly one of the reasons was because it's such a growing technique with so much potential. We wanted to see how it does.
More questions from the crowd? All right. I think you were sufficiently hard on Maria. So
thank you so much.
Say thank you one more time. So I'd like to excuse the crowd, the committee, and that includes you, Carl. Let's take a 5-minute break. If you would like to refill your drink or grab a cup of tea or anything like that, we'll do that. We'll clear the room, and then we'll proceed with the closed defense.